Okay, so we're going to do one more of the gas laws that we need to understand for this unit, and that is called the ideal gas law. It is the combination of all the laws that we have learned, and it helps us to approximate real gas behavior and can be used when not at STP, which remember STP is standard temperature and pressure. So we're going to incorporate lots of different variables here into one equation. And so first let's talk about some of those variables that are incorporated in an ideal gas law. And so we need to go back and look. This is kind of what we did before we went on break and what we've been talking about, just looking at a container of a gas. So what is this? This is a closed container. We can say this is all just one piece. We'll say for right now, this is also a non-flexible container. It cannot get bigger or smaller for our purposes of just discussing. So what's going on? We've got a particular volume, particular size, and that would be your V. So V is our volume. It's the container. It's how much space these particles are going to be taking up. And then all of the, we could also take the temperature. This temperature, it looks like there's a temperature gauge here on this container. And so what is the temperature of those particles? And remember, the temperature really is directly related to kinetic energy and how fast those particles are moving. Just like we saw in the last one in Charles's law, as we increase the temperature, it's going to be increasing the speed of these particles. And that's what these arrows are. They're the movement of these particles, because these particles are in constant motion and moving all the time, bumping into each other. And again, the hotter it gets, the faster these particles move. And if they do get hotter and move faster, then the pressure of this container will increase. Now, if this were a flexible container like a balloon, then that balloon would grow and grow and grow to try to equalize the inside pressure to the outside pressure. So we could, and speaking of pressure, we could have a pressure gauge on this to tell us how much pressure is in this container. And what is pressure? Pressure is the movement of these particles. It's how the particles are hitting the sides of this container. And that force, speed and force of hitting, how many times they're hitting the side of the container is what creates this pressure. And we've seen already in some of our formulas that pressure can be in atmospheres, it can be in torr, it can be in kilopascals. And so lots of different ways that we can write the units for pressure. Temperature, we're always going to have in Kelvin on these problems, and volume can vary too, milliliters or liters. Now, for our purposes on the ideal gas law, we're going to want that volume in liters. And we'll talk about R in just a second. So what is this N here? We've talked a little bit about it as already in some of our activities, but the N is the amount of particles. And so really, we haven't varied that amount at all. So when we talked about Boyle's law, we said, okay, well, we're manipulating pressure and volume, but temperature is staying the same in Boyle's law. Well, we didn't mention that amount of gas was staying the same, but it is. In both Boyle's and Charles, the amount of gas was not changing. And so that was staying the same. So now we can maybe even manipulate that and say, what happens if I blow more air into this container? Well, clearly, if I put more air in here, it's going to make some effects, right? More air, more particles in here, obviously we'll have more pressure, and depending on whether this is flexible or non-flexible will depend on what changes. And so the R, this is going to be a special number called the ideal gas constant. And so it's not a number that we'll have to figure out. It's a number that will be given to us. It's a number that we'll use in every formula. It'll always be given to you. And on a test or something like that, I will give that number to you. You won't have to worry about memorizing or anything. Okay, so there are 3 values of R depending on the unit of pressure. And so everything else has to always be the same. As I said, volume has to be in liters, temperature has to be in Kelvin, amount of particles is always going to be in moles, and that's how we typically measure. It's the easiest way for us to measure particles. And so this can change. We can have atmosphere or torr or kilopascals. And so we can have, because of that, we can have 3 different R values. And so it could be 0.0821 liters times atmosphere. I'm just using the dot to indicate multiplication. Liter times atmosphere over moles times Kelvin. So because that's atmospheres, you would use this one if your pressure is given in atmospheres, or if it asks you to give your pressure in atmospheres. This is the R value you would use. If you're given kilopascals, you would use this one, 8.31 liters times kilopascals over moles times Kelvin. And then the third one, 62.4 liters times millimeters of mercury is another one of our units of measure over moles times Kelvin. So that's also one of our millimeters of mercury. It's one I forgot to put on here. And millimeters of mercury and torr are always the same because there's one atmosphere is 760 millimeters mercury, one atmosphere is 760 torr. So we should have seen that in some of our conversions. Okay, so the formula that we're going to use is pressure times volume equals moles times R times temperature. Now I'm just setting these variables next to each other, but they are being multiplied. So pressure times volume equals moles times this R, which is your ideal gas constant, times your temperature. And so if we're missing any number of these, we can set our formula up differently. You can write these down if you need to go back to them. But let's say we're missing pressure. This is algebra. What would we do? We would want to isolate this variable. And so it would be, we'd divide both sides by volume. And so you'd have N times R times T divided by V. That would be how you would find pressure. Let's say we were trying to find volume. We would have to isolate the volume. So we would have N times R times T divided by the pressure. Okay. Let's say our N is what we were missing. And so we would have N equals, we would have to divide both sides by the RT to get rid of those two. So dividing the PV by the RT, I'd have N equals P times V over R times T. And then finally, if we had temperature missing, same thing, I'd have to isolate by dividing by the N and R, the PV divided by N and R to isolate that. So we would have P times V divided by, in this case, N times R. So you might want to write these down if the algebra somehow bothers you. You can have these kind of, especially to help you through some of the homework problems, but make sure that you know how to manipulate an equation to get your answer. All right, so let's look at a couple of questions here, and then you'll be on your own to try some of your own. So a gas in 4 liters. Now, one thing that you're going to notice here that's different from Boyle's and Charles is that we don't have like a P1 and a V1. We don't have a, so there's not a change. We're really just looking at a missing variable. So sometimes I'll just go ahead and list my stuff as I go, or I'll mark it in here so I'll know which variable it was that I needed. So a gas in 4.0 liters, that's my volume. Okay, that's my volume, and I don't need a V1 in this case because I just have one of each of these. Gas in 4 liters container at temperature of 22 degrees Celsius. So we should notice right there that we need to convert that to Kelvin. So how do we do that? We do that by adding 273. So that gives me 295 Kelvin. I can write that here. Okay, so now I've got my temperature, I've got my volume, and it says it has a pressure, 0.75 atmosphere. That's my pressure right there, my problem. And now I'm to that question, how many moles? That is my, oops, I already had it right here. That is my question. My N, how many moles, the amount of gas are there. And so my R, remember, depends on what I'm given in pressure, which is my atmosphere. So I can go back and I can look at my R values. This is 0.0821 that I'm going to be using for this one. So I could write it here. for my R value. And now I just need to plug those in and rearrange my equation algebraically to solve for my missing variable. So pressure, 0.75 atmosphere, times my volume, 4.0 liters, equals my amount is what's missing, so plug everything else in. And my temperature, remember that it does need to be in Kelvin, so don't accidentally come and grab the Celsius. Always make sure that you remind yourself that it does need to be in Kelvin. So sometimes there's a little bit of a struggle in our calculators with these, so I'll try to show you that. So we're just going to say this times this, and then divide it by each one of those, and that should give us our N. Okay, so we'll go 0.75 times 4.0 gives me 3. Then I'm going to divide by 0.0821 and go ahead and hit equal, and then divide by 298, hit equal just to keep it nice and clean. And then this is what I get in my calculator, and I'm going to be rounding that. Looks like 2 sig figs throughout here, so just need to round it. 2 sig figs, 0.12. So once I've done that, 0.12, and your unit here is moles. Remember the abbreviation for moles is MOL, and that is N. And there's the final answer. Okay, so let's try to do another one. If you wanted to pause or go back to look at that one, you can. Let's do one more of those. At least one more. Okay, so next one, number 2, 7.25 moles. So here I'm given my N, so 7.25 moles of air are pumped into a car tire at 80 degrees Celsius. So right away, we should recognize that we do need to add 273 to that, and that gives me 353 Kelvin, and I can go ahead and write that temperature down here. And the pressure inside that tire is 506.625 kilopascals. If you've ever taken a pressure, using a pressure gauge to see your pressure on a tire, okay, kilopascals. Now this one tells us right here which one of the R's we're going to use. So I could go back and look at that. I'm using the R that is the kilopascals, which is 8.31, and you will not have to memorize any of those. They'll be given to you. Okay, so there's my R. And so right now I can already tell what's missing, although usually the question is going to give that to you. What is the volume? So we can tell my volume is what I'm missing. So if I can memorize my PV equals nRT by the time you've written it so many times, hopefully you'll have it memorized. And then we're just going to plug everything in to that formula. So 506.625, quite a lot of decimals on that one. And my V is my variable that's missing. N, my number of moles, 7.25 moles. Plug the proper R in, 8.31. And the temperature that has to be in Kelvin, and plug that in there. Okay? Now, algebraically, we know that we need to isolate my variable. So in my calculator, I'm just going to say this times this times this, hit equal, and then divide by that to get my V alone, because these two are being multiplied by each other. So let's see what that looks like. 7.25, I'll put it to the side here. 7.25 times 8.31 times 353, and hit equal. That's what I should have in my calculator, and then I'm going to divide it by that, 506.625, and hit equal. And so my V should equal 41.13. Did I do that right? That looks different than my other number. Let me double check. 7.25 times 8.31 times 353, hit equal. Divide by 506.625. Yep, okay, did get it wrong. 41.98, rounding that up. Okay, so let's see if we can get one more of those done. And this looks like it really should have been 3 sig figs, so it might even round up to 42.0 if we're looking at sig figs there and my liters. And again, on some of this, you won't necessarily have to worry too much about the sig figs on a multiple choice exam.